All right, it's absolutely a wonderful journey working with all of you for this cool semester. I can have the mic. Okay, there you go. And let's have a quick course review. Right? So we've covered several aspects from inference to training, and then we have those application-specific optimizations, followed by those more advanced, future-looking quantum machine learning. And basically, these are the three big components, including efficient inference, training, and application-specific optimizations. And we try to teach you those high-level concepts. So today, in this review session, hopefully give you some big pictures. And then across algorithm and system co-design, across ECS and AI+D, these are the related courses. If you want to continue exploring related area, those are some wonderful courses you can consider taking in the future. So part one, we talk about efficient inference techniques, including pruning, quantization, neural architecture search, and knowledge distillation. And so pruning, basically, we can safely remove lots of the connections in the neural net without hurting the accuracy. And lots of you have made wonderful presentation. You explore different characteristics beyond the efficiency characteristic, which is very awesome. And we can also prune across different granularities from this fine-grained pruning, where we can do more, to this coarse-grained pruning, where we can prune less, but easier to accelerate. And NVIDIA is using this 2-to-4 sparsity natively in their GPUs these days. We also talk about this sensitivity analysis, where how to decide how much we prune for each layer. Right? So this is a semi-automated approach to decide the pruning ratio. And as a result, we can now plot this curve with the accuracy and with the model size and accuracy trade-off. Right? With iterative pruning, we can achieve the fast trade-off between the accuracy and the model size. So after pruning, we talk about quantization. Right? We don't need full precision to represent a neural net, right? but rather we can use very few number of bits, like 4 bits or 8 bits, without losing the accuracy. And there are several approaches to do quantization, including k-means-based, which is most flexible. Linear quantization, widely used in our mobile phones these days, and even ternary or binary quantization. Right? So k-means quantization basically is doing a k-means cluster to find those centroids. And when we are doing the update, we group them by their group and then multiply by the learning rate subtracted from the original centroid. So we can do quantization aware fine-tuning. For linear quantization, we introduced these 0 point and also the scale. Right? So minus the 0 point times the scale. And notice the scale is very important during on-device training. We are using this scale to do quantization aware scaling to enable training on real quantized graph. Even more aggressively, we can make both the weight and activation to be binary alternate. Right? So the modification add becomes a pop count, which is very easy to implement by hardware. Okay, to summarize, these are the efficient inference techniques. We also talk about the neural architecture search. So rather than manually design those neural nets, which is very cumbersome, to tune the different dimensions, layers, channels, kernels, okay? We define a search space and define a search strategy, maybe reinforcement learning, maybe evolutionary strategy, and then have a performance estimation strategy, like either using flops or using those proxyless characteristics, like direct measurement of the energy, of the latency, etc. And finally, we can run, for example, evolutionary search to give a particular latency accuracy budget and find the best sub-neural networks. In our homework, we work on this wide-for-all network. You can design one model that can contain many sub-networks that can fit different hardware constraints, like a bigger subnetwork for a newer chip, powerful chip, and a smaller subnetwork for an older chip. And the benefit is that for wide-for-all network, You don't have to train multiple different models, but just one model. And you can have multiple different subnetworks that can be specialized for different hardware platforms. Also, we can use that for full battery scenario and also the battery saving model. And apart from this neural architecture research, we also talk about distillation. Right? We have a teacher network, which is usually larger, student network, which is usually smaller. We want to teach the student by mimicking those logics. We can not only mimic the logics, but also try to match the intermediate activations of gradients. Okay, we can define different distillation losses. Okay, then we switch gear from inference to talk about training. First, on the cloud with multi-node, multi-GPU distributed training. So remember, there are two parallelisms. We can split the data. We can also split the model. Okay. Split the data, we call it data parallelism. And if you split the model, layer 1, layer 2, layer 3, that is the model parallelism. Okay. Sometimes the model is just so big, we need both data parallelism and model parallelism. And as communication is required during multi-node distributed training, the bandwidth is a big bottleneck, including memory bandwidth and networking bandwidth, since the gradients need to be exchanged among the network. Right? So here we learn techniques to optimize and reduce the networking bandwidth for large-scale distributed training. For example, we can prune those gradients, okay? And also we can quantize those gradients so that we can send less gradient over the network. For example, here we learn about deep gradient compression, where only 1 in 1,000 gradient actually needs to be sent out. Right? So here we need to correct the momentum, okay? Do a momentum correction to make sure there's no loss of accuracy. Another big issue apart from bandwidth is the latency. As the latency increases from a few milliseconds to 1 second, the speed drastically decreases. Right? So we learn about this delayed gradient averaging technique, okay, to tolerate the long latency. You don't have to wait until the gradient you receive the gradient, but you can directly move forward even before you receive the gradient and tolerate such stale gradient. It's like submitting the homework utilizing the late phase. Okay, you utilize 4 late phase, and still it can converge. Finally, we learned about this speed up using 8-node Raspberry Pi, showing the effectiveness of these methods. So apart from training on the cloud, we also learn about techniques for on-device training and learning on the edge to enable this always-on lifelong learning, and enable customization and make it privacy preserving, since users' private data like their speech, their voice, their mails, or their photos doesn't need to be sent to the cloud. But that is very challenging. Right? That preserves privacy, that is enabling customization, but on-device training is limited by the memory, where we have to store those intermediate activations. Right? So we learned some techniques like tiny transfer learning, TinyML, to fine-tune those bias, where fine-tuning the bias doesn't require storing any intermediate activations. And apart from that, we also learn techniques to translate the algorithm improvement to actual saving with algorithm and system coding. For example, using the Tiny Training Engine, which we recently open sourced on GitHub. You can use quantization aware scaling and also sparse layer, sparse tensor update to only update a subset of the models. So we cannot directly scale a model designed for mobile inference to mobile training, right? Since they are fundamentally different. Therefore, we need to design the new techniques such as quantization aware scaling and sparse layer, sparse tensor updates. And in our experiment, we discussed a small and dense model is less good as a large and sparse model. And finally, we discussed these application-specific optimizations that are computationally intensive, including point cloud, widely used autonomous driving. Right? So we take advantage of those spatial sparsity, spatial redundancy to optimize and accelerate that. And the videos, which has this temporal dimension and adjacent frames are very similar. So we want to take advantage of those temporal redundancy. We use a temporal shift module to use shift rather than convolution to accelerate video understanding. For these CAD models, generative models, we can take advantage of the spatial redundancy. If you just make a small change, you don't have to redraw the whole image. For natural language processing, where human language is inherently very redundant, you can take advantage of the token redundancy, remove the words from the sentence, and you can still understand the meaning of the sentence. And finally, we'll give some futuristic, talk about some more research stuff about quantum machine learning, introducing the basics of quantum circuit, how is quantum machine learning executed, and how to overcome the noise to make quantum ML noise robust. And we could have 4 labs about pruning, quantization, neural architecture search, and finally we deployed the model on microcontrollers. And hopefully this code base can help you for your future research, even not for the efficiency purpose, but try to explore the other aspects of efficient and compressed model. Finally, thanks to our industry partners, for example, STMicro, who is donating us those microcontroller board. Don't forget to return them so we can reuse that for next year's lecture. Thanks to Qualcomm, who's going to give us a guest lecture in a moment. And OmniML giving us a guest lecture, and also I'll offer the early access to Optimizer, which have shown very effective. And if you need to have a longer license, feel free to contact us. Thanks to Google providing us the computational resource. And finally, thank you so much for working with me for this whole semester on this new course. This is the first time this course is being offered, and I really hope our 5 years, 6 years of research can be condensed into a whole 1 semester of lecture. So it might be running pretty fast, a lot of pouring a lot of knowledge into our brain within a short semester. But I really appreciate the positive feedback during the reviews and all the participations and amazing project reports that I find super exciting.